Welcome to Your Space Journey, where we venture into the future of space exploration and the incredible leaders who are taking us there. Here's your host, Chuck Fields.
Hello, thanks for joining me today. NASA has just selected a new mission to study giant space weather storms from the sun. The new mission, called SunRISE, stands for Sun Radio Interferometer Space Experiment. This mission will ultimately help protect astronauts traveling to the Moon and Mars by providing better information on how the sun's radiation affects the space environment they must travel through. Joining me today is the principal investigator of the SunRISE mission, Dr. Justin Kasper. Justin is also a professor of space science and engineering for the University of Michigan, where he designed sensors for spacecraft that explore extreme environments in space from the surface of the sun to the outer edges of the solar system. Before we get to my interview with Justin, I want to introduce our segment called Your Space Journey. This is where we invite our audience, that means you, to call in and let us know what you love about space and what you're most excited about for the future of space exploration. Today it's my privilege to introduce my friend, Stacey David Severn from Star Talk Radio.
Hi, I'm Stacey David Severn. I'm with Star Talk Radio. You know, my earliest memory was always seeing spaceflight on the TV, rocket launches, EVAs. By the time Apollo 11 rolled around and we were walking on the moon, I remember clearly we were visiting my cousins in New Jersey. It was late at night and I was tired, and my parents made me sit in front of the console TV, and we had just gotten a color TV back then, sitting on the floor and saying, you know, you're going to stay up for this because they didn't command me, but you'll remember this for the rest of your life. I just remember those words and seeing the men walk on the moon. And so I think, you know, in addition to going further out and finding places that would support life or may have life already, the way to get there, I think, is very exciting. And it's just really cool to watch all of these great ideas and see them hatching and see how they're going to go.
Your Space Journey.
Thanks, Stacey, for sharing your story. Again, we'd love to hear yours. Just give us a call at 317-862-4700 or email us an audio or video clip. Just send that email to info@yourspacedjourney.com. Justin, thank you so much for joining me today. Really appreciate it.
Well, really great to be here with you.
Well, I tell you, this is an exciting time. Now, you're the principal investigator for the SunRISE mission and also professor at the University of Michigan. I was wondering if you can tell us a little bit more about your background and sort of where your space journey began.
Sure. So as a kid, my first memories were making models of the Apollo and Gemini capsules with my father, and then watching the space shuttle taking off.
Nice.
And when those first Voyager images were coming in, I remember painstakingly printing them out and pinning them on my wall. I forget 100 baud modem or something ridiculously slow.
Right.
And then I was just really lucky when I went off to college. I knew I had to get a job to help pay for everything. And that first week there, I saw these signs up, "Are you interested in space? Like, come work in the space group." And there was a professor there, John Simpson, who was a pioneer of high-energy particle or cosmic ray research. He started in the Manhattan Project and then took the detectors they invented there and put them on balloons and helped show that solar flares can actually produce radiation at high energies, particles traveling nearly at the speed of light.
Yeah.
You could just detect them from the upper atmosphere. So plunged right in there and started working on space and never looked back.
That's wonderful. Now, here you are. As we said, you're the PI for the SunRISE mission. I just wondering, can you give our audience just kind of a big picture view of what is the SunRISE mission about?
Right. So one of the biggest threats astronauts and our satellites in orbit face is every now and then the sun will suddenly release a giant burst of high-energy particle radiation. So this is charged particles originally from the sun's atmosphere that have been swept up in a solar eruption. Some of you might have heard of solar flares. There are also these events called coronal mass ejections, where a chunk of the sun's atmosphere that weighs about as much of Lake Michigan will go from rest to moving at a few million miles an hour in just tens of minutes. And as that plows into space, it can produce this particle radiation, which can destroy electronics, on satellites, and it can give astronauts harmful radiation doses. So we know that these eruptions from the sun can produce those events, but we're pretty lousy at predicting whether or not an event is going to produce the radiation, whether or not that radiation is going to reach Earth. And SunRISE at a high level is going to try to answer that question. We're going to use a cool little trick to try to be able to observe where acceleration and radiation happens for the first time.
I want to dive in a little bit more about that. Because one thing that I actually made the mistake of is coronal mass ejections versus flares. I initially thought they were the same thing. What fascinates me is I understand that CMEs actually take longer to reach Earth. Can you tell us a little bit more about the differences and just how long it takes to reach them?
Absolutely. And by the way, you should not feel bad about confusing them. I mean, even in our community, it took decades to appreciate that they were different things, and even longer to appreciate that actually those coronal mass ejections might be the more dangerous event in certain circumstances.
Yeah.
So a classical solar flare is when there's an explosion right on the surface of the sun, and you get a burst of X-rays, gamma rays, visible light, and also sometimes particles accelerated to high energy. That happens at a kind of localized point in the sun's atmosphere. Often after a solar flare, which involves the release of a lot of energy, materials released into space, and that pent-up energy can turn into one of these coronal mass ejections. But sometimes you don't really see a big solar flare, and a large coronal mass ejection will lift off from the sun. So they don't always happen one after another, which is a puzzle we're trying to solve.
Wow.
But these coronal mass ejections, I like to think of it like if you ever took a spring and squeezed it with your fingers, and then sometimes that spring will just bend and come flying out. Well, the sun's atmosphere can twist all this magnetic energy into almost a spring, and that spring becomes unstable, and it goes shooting out. And as it goes flying away from the sun, and it grows in volume. So by the time it reaches Earth, it might be filling maybe a quarter of the inner solar system. And so that thing is moving very quickly, but only at maybe a thousandth the speed of light. It can take a day or two to get to us. The high energy particles can reach us in 8 minutes. They're traveling at the speed of light. And one of the problems is you can see a solar flare or coronal mass ejection in visible light 8 minutes after it happens at Earth. Okay. And these high energy particles arrive right after that. So there isn't a really good warning for astronauts to take shelter or to power down critical systems on satellites so they can survive an event like that.
See, and that's amazing. Now, you mentioned obviously this can harm astronauts as they go to the moon and onto Mars. Can you tell us a little bit more about how does it harm them? Is it more electronics? Is it physical?
So for satellites, all the electrical parts, the microchips, et cetera, those semiconductors, that can get damaged by these particles passing through the material, and sometimes damaged in an irreversible way. So you can just lose. We've lost multi-billion-dollar communication satellites from these particle flares events. And it turns out if you just power things off, there's a much higher chance that they can survive. Really? And as much as we don't want to ever have a gap in our XM radio or television, I think we'd be willing to trade a couple hours out for the satellite to survive. And yes, the military has the same challenges. For astronauts, it's just straight up radiation dose. So think of your Geiger counter and trying not to be exposed to radiation. Astronauts, if they have enough warning, they'll take shelter in a part of the International Space Station with heavier shielding to try to protect them. If astronauts are on the moon, we would try to have a little area behind a rock or something they could try to scramble behind.
Right.
And so that advanced warning just allows them to take shelter.
Okay, well, let's talk more about SunRISE and how that advanced warning is going to be caught. What I understand is it's actually going to form sort of a virtual dish about 6 miles across. Can you tell us more about how that works?
Yeah, I love the technology behind SunRISE. So our motivation is for something like 50 years now, we've been sticking antennas on satellites when they go into space. And we can look at low radio frequencies. For those that are interested, I'm talking AM down to shortwave and even lower than that. So 20 megahertz down to just hundreds of kilohertz. So we're talking wavelengths that can be miles long.
Right.
And those can't make it through our atmosphere. That's actually why shortwave radio works. If you're on Earth, shortwave radio travels long distances because it goes up and then it basically reflects off our upper atmosphere. Well, outside in space, you can get these radio waves, they can't make it in. We know from the single antennas that whenever there's a major radiation event about to happen from the sun, as one of those eruptions is moving away from the sun, about 10 or 20 minutes before the intense high-energy radiation that would harm a satellite or an astronaut happens, something around that eruption begins to glow in low-frequency radio waves. And it's so intense, it's almost like a laser process happening. It's incredibly bright, it's at a very narrow frequency, and it briefly, for minutes, outshines the rest of the universe. And what we think is happening is that burst, that laser-like radio emission is happening because electrons are starting to get energized. They're beginning to stream away from that eruption at higher energies, and that makes radio waves start emitting from that region. And then 10 or 20 minutes later, it steepens. Something gets stronger, it crosses a threshold, and now all those high-energy ions are also being accelerated, and the really threatening event happens. So the problem is, we just see that in time. We have that timeline, and it's very consistent, but we can't image it yet. So if we could just image where that burst was coming from, we'd be able to tell what part of that coronal mass ejection is the source of this radiation, both the radio waves, the electrons, and those dangerous ions. So we want to image it for the first time and just say, like, well, what part of the eruption? Is it the front, the back, the fast part, the slow part, the big part, the little part? We don't know these basic things. And so you just look at the wavelengths of light you're looking at and take the equations for how big a dish you need or a lens to focus that into an image. And you wind up needing a dish that's about 6 miles across.
Wow.
And I would love for us to be building 6-mile-long structures in space, right? But we're not really there yet.
No.
And if you could imagine, even if you could build a 6-mile dish, turning it to like point at the sun, would require a tremendous amount of energy. So for decades, what people have said is, if we could just build a bunch of small satellites, put an antenna on each of them, and measure the waves coming from the sun exactly, like coherently at all of them, on the ground we could combine those waves and actually reconstruct an image. It's the same way radar works. The problem was always, 10, 20 years ago, you'd say, I want to launch a whole bunch of spacecraft. I'm going to build a lot of identical satellites. People would say, you're nuts. Like, you have no idea how much that will cost. You can't just mass produce spacecraft. And the signal processing was just too challenging also. And so, now we live in an era, while we were proposing this, like SpaceX started launching 60 satellites at a time. We were like, see, we told you it was possible. And so one of our secrets is building a bunch of very simple spacecraft, but then they fly in kind of a cloud about 10 kilometers or 6 miles across, and convincing people that we know how to mass produce satellites now was one hurdle. The other thing, if people are interested in geeking out a little bit, the other challenge was just in the past, like you would just have to record volumes and volumes of data. We were talking like terabytes of data a day, and it just wasn't clear how you'd even get that down to the ground. And our trick is we use the signals that come from GPS spacecraft. So what you use on your cell phone to navigate, if you're using your map program, your cell phone's actually receiving time codes from a bunch of different satellites, figuring out like the difference in time for the signals arriving, and therefore determining exactly where your cell phone is. Well, our satellites have GPS receivers on them, and so they figure out where they are in the constellation, and they trigger to take data at the exact same time using those timestamps. And that removed all these hurdles of technology, figuring out where you are on your own and all that. So it's really cool. We're taking advantage of some really awesome technology to enable this.
So you're using 6 CubeSats, and these satellites are literally smaller than a microwave oven, about the size of a toaster oven. So what an amazing feat. If I understand right, you really only need 5 to do it, but you're doing 6. Is that just for redundancy, an extra one?
That's right.
Okay.
NASA loves to see redundancy, right?
Sure.
And the wonderful thing we realized was, so imagine trying to figure out where emissions coming from on the sky. How would you describe that? Well, you'll need like two angles to map exactly where it's coming from.
Mm-hmm.
Maybe you want to describe how wide the emission is in two directions. So that's another two variables. And maybe you want to know how bright it is. That's about 5 variables.
Wow.
So it turns out if you have 5 spacecraft, they're actually measuring, when you're comparing the signals arriving between them, they're measuring more than 5 unique quantities. But 5 spacecraft lets you measure those parameters robustly. If one of those failed, we'd go down to 4. We'd still be able to do our basic science. But so our thought was, let's plan on launching 6. And then if something goes wrong while you're commissioning, you go down to your 5. But also on the ground, if we're running into a problem with schedule or we've run out of money and we want to stay on budget, we can just ditch one of those satellites. And the great thing is, you could shut it off in space and still save money. You could shut it off on the ground. And now if you're sitting there and you're thinking, but NASA has so much money, like why is Justin worried about, budget and saving money? One of the wonderful things about the program we're funded in, it's called the Explorer program.
Yes.
And the Explorer program is really exciting. It's one of the programs NASA has where you as a principal investigator, that's my position on this project, you send them a proposal for a certain amount of money. And they go, okay, good luck. There's your money, right? And then it's on you, if something goes wrong, to figure out how to make changes and respond to keep in that budget. And in exchange for you agreeing to take on that responsibility, you're afforded a lot more flexibility. So we report to NASA everything that's going on, but they don't really tell us what to do as much as we would on like a $1 billion mission where it's like, look, everything has to work. We're not going to like try again next week if something goes wrong. So it's riskier, but you have to figure out how to manage your own budget and schedule, in exchange for being given that freedom.
I'm really impressed, Justin, because this mission, again, it's only like 62.6 million, which to me, when I looked at that seemed relatively low cost, which is fantastic. So you've got the $62.6 million budget. You've got a launch date scheduled for 2023. So if I can ask, as PI, yes, it's great that this just got approved, but this is when you really have to roll up your sleeves and really get to work. So is this sort of now the busiest time for you as you go into this mission?
Well, it'll get busier and busier as time goes on. One of the fun things being principal investigator is you're busy when you're building the hardware, and your science team's just kind of in part twiddling their thumbs waiting for launch. And then you're busy after launch when the engineers are like, well, success, let's move on to the next project. And the scientists are like, now it begins.
Wow.
So yeah, we're entering into now a very intense kind of 10-month-long phase where we begin all our contracts and long lead procurements. So by the end of this 10 months, we'll know exactly which rocket we're launching on.
Nice.
We'll have started buying things like our solar panels, started manufacturing the spacecraft. And then the next phase after that will be a very intense kind of 1.5 year period where we're building 6 spacecraft at the same time. And you mentioned the budget is small.
Yeah.
I mean, I'll tell you something else. So we have to buy 6 spacecraft. When you normally hear about a lot of these missions, NASA pays you to build the spacecraft and the instruments, and then when you're done, you deliver them to NASA, and then they put it on a rocket and they launch it.
Right.
And that cost is handled by NASA. Another thing that's unique about this project is we're actually buying our own launch in part of that budget.
Really?
We partnered with a communications satellite company, and they launch communication satellites every month or two, and they usually use the same design, and there's a compartment on the back that used to hold a rack of batteries that they don't need anymore because batteries have gotten more efficient. And so this like $1 billion communication satellite is going to go up into orbit, and then it's going to shoot the 6 of our satellites out of its rear end, basically. And then it'll descend back and begin its operations. It's just a commercial satellite. The people using it will never know that it also had a secondary objective launching these little satellites, but it's a way for them to make a little bit more money out of their launch and for us to get really incredibly cheap access to space. I mean, it's like an order of magnitude cheaper than it would have been just a decade ago.
Justin, again, I'm so impressed. I would love to follow up with you as this mission goes on. So, but thanks again for joining me today. Really do appreciate it.
Awesome. Thank you so much. Take care.
You too.
Your space journey.
Wow, I really enjoyed my conversation with Justin today, and I'm really excited about the upcoming SunRISE mission. If you'd like to learn more, just go to their website at nasa.gov/SunEarth. I want to thank Justin for joining us today. I want to thank you for joining us as well. Again, we'd love it if you'd share this episode with a friend, but we, again, really appreciate you joining us today. We'll see you next time. God bless.